Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide an example of how to apply Newton's second law and to see how Newton's second law kind of goes hand in hand with the ability to study the motion of an object here. So what we're looking at, imagine this child starts there at the position shown on this sled, and we're going to imagine this example that the child starts from rest. So I'm going to put an initial velocity of 0 meters per second, and the child accelerates down this incline, this 10-meter incline, and we're going to imagine that that child gets to the bottom after 5 seconds. And what we're going to do now is we're going to try to calculate, or at least estimate, some sort of frictional coefficient between the sled and the surface of the incline. Right? So as we kind of look at this, some things to consider. We've got this distance, this 10 meters, in this time frame here. So we may start by kind of analyzing the motion of the sled, or the sled-child combo. Ultimately, what we'd want to try to get out of that is the acceleration, because once we know the acceleration, we can draw a free body, apply Newton's laws, and basically relate that to the frictional force and then the frictional coefficient. So let's start by analyzing the motion of the sled. So I'm going to start with a velocity graph. So again, that's just a quick plot of velocity against time. Right, so velocity against t. Now, at t equals 0, I'm going to call this time frame t equals 0. Sled's not moving yet, so we've got a velocity of 0 at that time. Now, 5 seconds later, the child's at the bottom. The velocity vector is down and right. It's equal to some v. I'm going to go ahead and call that v final. I don't know what that is, but I do know it is some positive value if I call down and right positive. So on the graph here, 5 seconds, the v final is this distance on the graph, but we don't know a value yet. I'm going to go ahead and assume constant acceleration along this path here, which means my velocity graph here is going to be linear. And what I want to get is the acceleration, which is the slope. So that's an easy thing for me to write down. The acceleration is equal to the slope of a velocity graph. Now in this example, that's going to be v final over the 5 seconds. But we don't know the v final, so this we're just going to have to put on hold for a moment. The other property of this graph that's pretty useful, this area right here, this triangular area, is equal to the displacement, which in this example is 10 meters. That's going to allow me to write a quick, easy equation for this. 1/2 times 5 seconds times v final. Now I'm getting that's the area of this triangle right here, is got to equal the 10 meters. And if I go ahead and solve that for v final, let's see, 20 over 5, 4 meters per second is what comes out of that. So the child should get to the bottom here at around 4 meters per second, moving at around 4 meters per second, which means our acceleration, if I go ahead and put the 4 meters per second in, should be approximately 4 meters per second over 5 seconds, which is 0.8 meters per second per second. All right, so we now know the child's acceleration. I'm going to go ahead and take all of this stuff and just maybe shrink it down a little bit. I'll leave it up here though for reference. Now the next part is, all right, how do we take this acceleration here and link it to the frictional coefficient? So that's where a good free body diagram will come in handy. So I'm going to imagine the child here, and I think what I'll do is I am going to kind of clone this. I'm going to draw my free body right here, kind of an intermediate picture here. Put them right here. All right, and I'm going to start putting force vectors in. First force vector I always put in a free body is, at least in physics 1, here's the gravitational force. So that vector is straight down, equal to mg. Right, surface in contact, that's going to give us a normal force. And again, normal is just kind of a funny word for perpendicular, so that force vector is going to act all along this line. I'm going to go ahead and draw that force vector right here. There's my normal. And again, the normal is referring to the right angle. Presumably here there's friction in this problem. Friction always opposes motion, and the friction acts along this surface. So the frictional force vector in this problem would be kind of up and left. That's going to be a little hard to see. I think what I'll do is, that's probably good enough. Whoops. So there's my force vector for the frictional force. And that's pretty well it. I don't see any other forces here to worry about. All right, so as we, geometry. The angle between the normal and the mg is typically pretty important. So this is 33 degrees. That makes this one right here 67 degrees. And then from here to here is 90. So that's going to make this one also a 33-degree angle between the normal force and the mg. So I'm going to go ahead now and write some force equations for this free body. Anytime you're dealing with the frictional force, you're probably going to need the normal. So first thing I'm going to do is go after the normal force. Now before I write the equations, we should choose a set of coordinates to work in. And what I'm going to do, and I'm going to put these coordinates in green, I'm going to go ahead and call this the positive x direction. And perpendicular to that, the positive y direction, kind of up and left. So y, x. My rule of thumb is this for choosing directions. If you can identify the acceleration, call that positive. So that direction positive. In this example, this person no doubt is accelerating this way. That's why I align my positive x-axis with that direction. That's a really good rule of thumb, works really well for writing Newton's second law equations. So I'm going to go ahead and now write a pair of equations. First, the sum of all forces in the y direction, and I'm calling this the positive y direction, is equal to 0. Now, in general, Newton's second law is net force equals ma. However, this child's acceleration does not have a component in the y direction. So the ma term would be 0. So I look over here, write that equation. I notice that the normal is in the positive y direction, so plus n. Okay, the mg. Now you got to think about that in terms of components. I'll go ahead and draw these in red. You can think of that as having a component this way, and that's what I would call the y component, and another component this way. Oops. Right. So this force component right here is parallel to the y direction. That component is adjacent to the 33-degree angle. So for that guy, I'm going to put minus mg cosine of 33 degrees. The minus sign is because this vector component is down and left, and I've got up and right positive. All right, that's it. The frictional force does not have a y component, so this equation is done. So equals 0. So our normal force in this example is equal to mg cosine 33. Now, if I had a mass, I could calculate a number at this point, but I don't, so I'm just going to move on. Next equation to write, sum of all forces in the x direction is equal to ma in the x direction. I'm calling this down and right the positive x direction. So I look at my free body and I notice the normal does not have an x component, but the mg does. The component of this gravitational force that's in the x direction is here. That vector component is opposite the 33-degree angle, so its magnitude is going to be mg, that's the hypotenuse, sine 33, and it's down and right. So I'm going to go ahead and put plus mg sine of 33 degrees. Now this plus sign here is, I just put it in there to make a point that I've considered the direction, it's down and right, and that is in the positive direction. You could actually leave that off. If you don't have a sign in front of a term, it's assumed to be positive. Next force vector, the normal, is kind of covered up by that vector component, but the normal does not have a component in the x direction. If you want to put a +0 here, you can, but I'm just going to leave it blank. And then we have the frictional force. Now the frictional force does not have a y component, only an x component, and it's in the -x direction. So I'm just going to put -F for the frictional force, and then equals ma. All right, so there's our 2 Newton's second law equations, 1, 2. Next, we're going to kind of combine them, right? The frictional force. So hopefully, maybe if you don't know something about friction, you could go back and review my videos about friction. The sliding frictional force is proportional to the normal force. And the proportionality constant is what's called the coefficient of friction. Specifically, it would be the coefficient of sliding friction in this example. I'm just going to leave it mu and call that good. So what I'm going to do is just go ahead and sub this term into this equation. So this is now going to read mg sine of 33 degrees minus the coefficient of friction times the normal. And I'm going to go ahead and put this in for the normal force. So that's going to be mg cosine 33, and then equals ma. All right, so we've got our Newton's second law equation now, or we got the results of it when we take our 2 independent Newton's second law equations and kind of combine them. And what we have here is an equation now that's going to allow us to calculate this, that frictional coefficient right there, which is what we were looking for. First thing to notice is there's an m in each term, so these divide out. So I would say, why don't we leave this term alone, g sine 33, and add that term to the right. So that's going to equal acceleration plus the coefficient of friction times g times cosine 33. Next, we're going to want this term on the left. And then the last step, we're going to want to solve for the coefficient of friction. That means we want to divide by this guy. My computer system's kind of cool for this, so what I'm going to do is just put a division, and I'm just going to do this. When you divide both sides by cosine 33, that's effectively what you're doing. What I would do here is pause this for just a moment and find myself a calculator here and calculate a value. Okay, so that didn't take long at all. I got a value of 0.55 for a frictional coefficient. Now you notice I didn't bother putting any units there. That's because the frictional coefficient is a dimensionless quantity. It doesn't have any units. You know, unit-wise, if we look at this equation, sine 33 and cosine 33 are dimensionless, and g over g, well, the units would obviously cancel. And acceleration units over g. Again, this has units of meter per second, and so does this. So the units cancel both sides of that thing. So what this means, it doesn't mean that the frictional coefficient is 0.55 everywhere. You know, conceivably that frictional coefficient varies along this location. That's pretty common. What it means is the average frictional coefficient between the sled and this surface is 0.55. You know, some parts of the trip maybe it's a little higher, some parts it's a little lower. So important parts of this problem: 1, how to analyze the motion of the child given the initial velocity, the distance, and the time. In this case, we started with a velocity graph. And some problems require a bit more complex math and writing equations, some don't. Typically, when you know the time, if you just put that along this axis here, you end up with pretty easy calculations for both slope and area for the displacements. Second, how to draw the free body. So that's a very important part of this problem. It's probably the most important part of this problem. And third, how to use your free body to write force equations. In this case, we wrote a force equation for the y direction where the acceleration was 0. And again, that's because of our choice of coordinates here. If that coordinate system was oriented like this wouldn't be 0 here because the acceleration would have a y component. But working in a rotated coordinate system, and again, my advice is always align one of your axes in the direction of the acceleration. That will usually yield you the simplest Newton's second law equation. So this allowed us to write this force equation equals 0 and get the normal. Then we wrote a force equation for the x direction, again calling down right the positive x direction. And there's our second Newton's second law equation. Combining these coupled with the how the frictional force relates to the normal yields the following equation, and out comes 0.55. So this video is getting a little long. I think I'll stop it there. I hope that this helps demonstrate how to apply these concepts. Have a great day.